So in the previous video, we have linked the Kelvin-Planck device to something that is possible. Kelvin-Planck device was not possible because entropy generation that was determined from the combination of first and second law analysis revealed that we have negative entropy generated, which renders this device not possible. But when we add a component to the Kelvin-Planck device, a heat removal unit, so I will draw it here, that we are going to absorb energy. We are going to absorb energy from a hot source to our device that operates in cycle. The cycle is going to generate work, but we need to discard some of the heat to the environment, which is at T sub C, in order to come back to the point that we have started. So the critical point here to notice is the fact that we need to remove heat in order to complete the cycle. All right, so here we have a heat source at T hat relieving Q hat to the cycle. The cycle generates work, and some of the energy has to be discarded to an environment which is at a lower temperature in order to come back to the starting point. All right, so this is going to be described in detail when we are learning Carnot cycle. But before I move to the Carnot cycle, we have also derived that the efficiency of the cycle in a black box mode was the difference between T hot minus T cold divided by T hot multiplied by 100% efficiency. All right, and the general description of the efficiency of the cycles is minus work divided by net work divided by the heat absorbed from the hot source multiplied by 100. So we use this to derive that. Now we are going to learn the Carnot cycle that is going to be reflected on this concept, but it is going to have 4 steps that are going to be reversible, and those 4 steps are going to make up a complete cycle. So let me draw the Carnot cycle on a PV diagram here. That we are going to have an ideal gas confined in a piston and cylinder assembly. Here is our piston and cylinder assembly. Our ideal gas is confined in this piston and cylinder assembly, and the ideal gas behavior is going to prevail throughout. Our Carnot cycle is going to have 4 steps. So I'm going to have 2 diagrams. One is going to be PV, and the other one is going to be TS, temperature entropy. Okay, so on a PV diagram, a constant temperature line for an ideal gas looks like this. All right, so this is T hot. An ideal gas has a reciprocal relationship between pressure and volume at constant temperature. Similarly, we have another isotherm at T cold, running like this, and this T hot and T cold are connected to each other by lines we are going to identify in a moment. So we have lines. We are going to identify those lines, what they are. I'm going to label this as state 1, state 2, state 3, and state 4. Now, I'm going to define each and every step one by one. Now, my gas, which is at state 1, low volume, high pressure, it's compressed severely to the fullest extent, expands reversibly and isothermally. Now, if a gas expands, it loses its internal energy Internal energy of an ideal gas is only a function of temperature, hence the temperature should decrease. But in order to keep this temperature constant, we have to transfer heat from the environment to the gas. So, one more time. A gas which is going to expand is going to lose its internal energy by doing work to the environment. In order to compensate that internal energy, we need to transfer heat so that we can keep the temperature constant. So, in this step 1, going from 1 to 2, all right, going from 1 to 2, this step is isothermal. We have heat interaction, we have work interaction. So I'm going to write, this is a closed system. This is a closed system. For the closed system, let me write the energy balance and the entropy balance for the closed system in short here so that we will use them throughout. For a closed system, we have du over dt to be equal to q dot plus work minus p dv over dt. And this work is shaft work. Again, similarly, the entropy balance looks like ds over dt to be equal to q dot over t plus S generated. Now we are going to use them in different steps of the process, going from state to state to reveal the fact about this process. Now let's see. Let me label the process step as Roman numerals 1, 2, 3, and 4. This is how our cycle goes. So let me do the energy balance for step 1. Step 1 with Roman numerals. The step is isothermal. Hence, the U term is equal to 0. All right, this time the U is 0 because this step is isothermal. And my energy balance reduces to 0 being equal to Q dot minus P dV over dt. And we rearrange and integrate to obtain, for P, we substitute N R T H over V. And we rearrange to have Q over dt on the side N R T H integral dV over V on that side. And this is going to go from state 1 to state 2. This is going to take care of this, that this is the total heat. Q is going to be minus nRTH. I'll just remove the minus for the moment. nRTH ln V2 over V1. This is going to be equal to minus work between step 1 and 2. I'm going to prepare a table here, and I'm going to fill that table while I will just do my calculus here in this zone so that we will retain the information here. Then we will translate it to the diagrams. Let's see how things go. So I'm going to have the state, or let me have not the state, but the step. Let's have the steps. Let's have the steps. Thermodynamic step. All right. How much heat is exchanged? Notice that I'm not putting any dot on top. It's just the total heat exchanged in that step. I'm going to write the work. I'm going to check the internal energy change. And I need to check one more thing. I need a little bit more space here. I will say this is the step. Now I have Q, work, internal energy change. I will write the entropy change here. The new term that we have learned, the new state variable. So I will try to draw as accurate horizontal line as possible so that we will have a neat representation of information. We're going to put step 1, step 2, step 3, step 4, and for the overall process. We are at step 1. Heat is N RTH ln V2 over V1. N RT sub H ln V2 over V1. In the interest of space, I'm not going to crowd this row, but I will say that work is equal to minus Q. All right, this is Q, this is minus Q. All right, internal energy change is equal to 0. And do you remember the definition of entropy change? Entropy change. Entropy, definition of entropy was Q over T, but let us fulfill the requirement by solving the entropy balance also. Now, the virtue of the Carnot cycle, which I forgot to mention in the beginning, that this cycle is reversible. Very important to remember, this is a reversible cycle. And the condition of the reversibility that we learned in the previous video is that the entropy generation is 0 for reversible processes. Now let's write the entropy balance. ds over dt is equal to Q dot, now this is step 1. My temperature is T sub H, which is constant. Integration gives me delta S to be equal to Q over TH. Q has been obtained in the previous step as nRTH ln V2 over V1 divided by TH, cancels, and entropy change turns out to be Q over TH to be equal to nR ln V2 over V1. Entropy is nR ln V2 over V1. So this is step 1. I will take a brief break to clean the board to continue with steps 2, 3, and 4. Now in the second step, we have a reversible but adiabatic process. What we are going to do is to extract as much energy as possible from this gas while we are carrying our gas from the high temperature to the low temperature. Adiabatic expansion of an ideal gas. Now the temperatures are obviously going to change. We are going to have an adiabatic process. Entropy generation is 0 because it is reversible. Let's finish the entropy balance first. ds over dt is equal to 0. This is a conclusion that you must remember. For reversible and adiabatic processes, entropy remains constant. Delta S is equal to 0. Zero. Work is equal to this time delta U. And delta U for an ideal gas only depends on the temperature. And delta U is equal to N times CV star times delta T. T final minus T initial. All right, T3 minus T2. All right, work is equal to delta U. Delta U is equal to NCV, T3 minus T2. Entropy change is 0. Heat exchange is 0. Step 3. Now we have an isothermal process. This isothermal process is going to run through the same algebra. Entropy generation is 0. ds over dt is equal to q dot over t. du over dt is equal to 0. Shaft work is equal to 0. Q dot is equal to my p dv over dt. Work is equal to minus q. Let me call this q hat because we are running that heat through T hat. Work is going to be equal to minus q cold for this step. And it's up to you to go through the algebra, but the same logic will prevail. N R T cold ln V final, which is V4 over V3. Entropy change is going to be Q over T cold. We are running this at T cold. This is N R ln V4 over V3. Delta U is equal to 0 because the process is isothermal. The fourth step is going to be, again, adiabatic. And a reversible. Let me write reversible here also. For the emphasis, not all adiabatic processes are constant entropy, only adiabatic and reversible processes. What is a reversible process? A process that doesn't generate entropy is a reversible process. That doesn't waste energy, that doesn't waste heat. All right, so adiabatic and reversible is a constant entropy process. It's adiabatic, heat is 0. Work is equal to delta U, and delta U is equal to n CV star times T 2 minus T3. Now, of course, I'm writing the temperatures of the states, but T3 is equal to T sub C, T2 is equal to T sub H, all right, this is equal to T sub H, this is equal to T sub C. All right, temperatures of those states are also those temperatures of the paths 3 and 1. Now let's look at the overall process. Let's go with the fastest. Delta U, I'm going to sum 0 plus 0 plus NCV TC minus TH NCV TH minus TC. This is 0. This is an important conclusion that we have to carry forward. We're going to use this fact in analyzing the processes. Now, internal energy is a state function, and this process goes from state 1 to state 1. Therefore, the internal energy change of the overall process is 0. Entropy is a state function. Overall process is going to go from state 1 to state 1, and entropy change of the overall process is also going to be 0. Now we need to carry out the algebra for heat and work. For that, I need to clean the board. Now we are going to establish the ratio of V2 to V1 and V4 to V3. Now we said that for the overall process, entropy is a state variable, and therefore delta S is equal to 0. It has to be 0. But then equation doesn't show as such. Equation says that this is equal to nR ln V2 over V1 plus nR ln V4 over V3. Since this is 0, we are going to cancel those. We are going to cancel ln's. Now we are going to carry the algebra such that V2 over V1 is equal to V3 over V4. This is just a consequence of the overall cycle being reversible. Therefore, also it has nothing to do with the reversibility, that this is a cyclic process and entropy is a state variable. Therefore, it is going to remain unchanged through for a complete cycle. And for a complete cycle, entropy change turns out to be the summation of those two terms. And as a result, we have also related V1, V2, V3, and V4 to one another also. Now, using this, we are going to calculate the net work. Right? Net work is equal to minus Q hot minus Q cold plus delta U plus delta U of those steps. Let me call this delta U2, delta U4, but some of delta U's were 0, right? So we will calculate the net heat. Q net was going to be N R T sub H ln V2 over V1 plus N R T cold ln V4 over V3. This is Q net. But V3, V4 were related to V2, V1. So let's put things in place. So this V4 over V3 is going to be V1 over V2, which is going to be minus V2 over V1. Well, we have NR ln V2 over V1 T hot minus T cold. This is Q net. That the delta U's cancelled. This is going to be Q net. This is going to be work net. Work net is going to be minus Q net. In other words, we're going to have NR ln V1 over V2 T hot minus T cold. So this is work net. Now we are going to calculate the efficiency of this cycle. What is the efficiency? How much I spent, how much I paid for. What do we pay for? We pay for the energy that we provide at the high temperature, the coal we burn, the natural gas we burn, all right, the nuclear reactor that we operate. The things that takes place at T hot are the things that we pay for. So how much I paid for, what did I gain? I gained a network. What is this network? This network is the shaded area. All right, the shaded area. This is the network, which is equal to minus Q net. All right? Efficiency is equal to minus network divided by QH multiplied by 100. Okay, minus network is Q net. It's NR T hot minus T cold ln V2 over V1 divided by Q hot. Q hot. This is NR T hot ln V2 over V1. This efficiency is equal to T hot minus T cold divided by T hot multiplied by 100. And that was the efficiency of this ideal cycle that was on the board a while ago. All right, so this was the ideal cycle, which was reversible. We expected that to have an efficiency that was defined by minus work net divided by Q hot. The second law analysis in the previous video reflected an efficiency of this form. Now we see that that efficiency, percent efficiency, that percent efficiency is identical to the efficiency of the Carnot cycle. There is one more thing that I have to complete before I conclude this video, conclude this recording. Now let's also fill the TS diagram. We're going to start at state 1. We're going to have a constant temperature process at T hat. Okay? Between 2 and 3, we have a constant entropy process. Between 3 and 4, we have a constant temperature process. Between 4 and 1, we have a constant entropy process. All right? We have a constant temperature, constant entropy, constant temperature, constant entropy process. Those two entropies are different, of course, but this is the Carnot cycle, the ideal reversible cycle that sets the basis of comparison for all the possible cycles that are going to be operated between a T hot and a T cold. Now, when we have a power generation cycle that is going to be generating power due to heat, we are going to compare its efficiency against the efficiency of the Carnot cycle, and Carnot cycle is going to guide us whether that process is possible or not. Now, that's what second law is going to be useful. We are going to check the processes whether they are possible. We are going to check the processes whether they violate the laws of the nature. And of course, the second law also going to guide us to give us the directionality of the processes, in which direction the processes go. So an example of this is, for example, having two pictures of a glass full of water and glass broken, water spilled on the floor. When you compare those two processes and when you logically ask yourself which process, if those two processes are sequential, which is first, the obvious answer is the filled glass to be the first step, that the glass being broken and water spilled has to be second, because the opposite is not possible. And not everything is that obvious, so we use the entropy balance and we look at the processes whether they generate entropy or not to decide which direction the process should go. Now, also in the previous video, we have seen that the Clausius device is not possible. The Clausius device was a device operating in cycle and transferring heat from a cold object to a hot object in the opposing direction of the natural flow. We have done the second law analysis and the first law analysis. Combination revealed us that for such a process, net entropy generation is going to be negative, and that isn't possible. But you see, we have devices that operate and transfer heat from cold to hot, such as refrigerators in our kitchens, such as air conditioners in our living environments. Now, the virtue of these devices is that we have introduced an external action onto the cycle. This external action onto this cycle is going to be in terms of work. Let me leave the Clausius device not to confuse you, but I'm going to now draw the refrigeration cycle for you. Let me move it up a little bit to save space. So we have the same process T cold, T hot, device operating in cycle, Q cold, Q hot, but this time we introduce work from the environment. This is the refrigeration cycle. We plug our refrigerator to power, and as a result of the power, we have some work in the cycle. Because of that work, heat is transferred from a low temperature to a high temperature, but we have to force the energy to flow in the opposing direction. In other words, if things are going in the natural direction, they just do. If we want things to go opposing to the natural direction, we have to do work. All right? We have to lift against the hill. Okay, so now we have derived the Carnot power cycle. Now I'm going to derive Carnot refrigeration cycle. I'm going to do the whole analysis once more to show you that a power cycle and a refrigeration cycle are closely related. Now the Carnot refrigeration cycle. Carnot refrigeration cycle is going to run just in the opposite direction of the power cycle. We are going to expand at low temperature and compress at high temperature. So our state 1 is here. We are going to expand at constant low temperature, T cold, from state 1 to state 2. All right? And then we're going to move almost identical, but in the opposing direction, to the power cycle. All right? So we are now going in this direction. T cold. And now you understand that those lines are constant entropy lines. Okay? Similarly, on the TS diagram, we are going in the opposite direction. We start at low entropy, go at high entropy. This is T cold. S, T hot, S. So let's just work our algebra. This is process step number 1, number 2, number 3, and number 4. Okay? Step number 1, reversible isothermal expansion. Process is isothermal. As a result, internal energy is 0 because we have an ideal gas. There's no shaft work. Q is equal to nR T sub C ln V final over V initial. V final is equal to V2, V initial is equal to V1. All right? So Q is equal to nRT T sub C ln V2 over V1. Entropy change is Q over Tc, and that's equal to nR ln V2 over V1. This is minus Q for step 1. Step 2 is adiabatic. And reversible, isothermal and reversible, adiabatic and reversible. Q is equal to 0. Entropy change is equal to 0. Work is equal to delta U. And delta U is equal to N CV. T final is T hot. T initial is T cold. Second step. Constant entropy. The third step is again isothermal. Hence, internal energy change is equal to 0. Heat is equal to N R T H ln V final. It is V final V4 over V3. And this is equal to minus Q sub H. And this is equal to N R ln V4 over V3. Fourth step is adiabatic. And reversible, and reversible, and reversible. Such that the entropy change is equal to 0, heat exchange is equal to 0, work is equal to delta U, and delta U is equal to N CV T final, which is T sub C minus T initial T sub H. And again, same for the overall process. Entropy is a state variable. This is a cyclic process going from state 1 to state 1. Should not induce any change in the total entropy. Delta S should be 0. Internal energy is a state variable. It should be equal to 0. But from the analysis, we see that this is already 0. All right? And the change in the internal energy cancels out. Work is equal to minus Q net. And minus Q net is going to be equal to, again, we will use the overall entropy change to relate V2 over V1 to V4 over V3 to have a global expression. So from the overall analysis, we have delta S being equal to 0. This is equal to N times R times ln V2 over V1 plus N times R times ln V4 over V3. So from here we deduce, similar to the situation that we have done for the power cycles, V2 over V1 is equal to V3 over V4. Now for the net heat, we have NR ln V2 over V1. We are using this as our basis. T cold minus T hot. All right. Work is equal to minus Q net. Work is equal to minus that. Now, what is our performance criterion? We're not going to talk about efficiency this time. All right. Here, what we pay for is the network. What we gain is Q sub C. So we're going to derive a parameter which is called the coefficient of performance. And this coefficient of performance judges against what we get for what we have given into this process. In short, it will be COP. What we get cooling. That's our objective, Q sub C. What we give in? We give in network. We give in a network. Look, they are both pointing into the same direction. They're both going into the cycle. When they're going into the cycle, their sign are the same, therefore no need to put a minus sign, all right? And there's no need to put a percentage. Now let's calculate the coefficient of performance of this cycle. Q sub C is equal to N R T sub C ln V2 over V1 divided by NR ln V2 over V1 divided by T sub C over T sub C minus T sub H. There seems to be a sign mistake which we have carried from here, so let me see if we can find that sign mistake. V2 over V1 is equal to V3 over V4. From here, there is no mistake here. We haven't carried out the algebra appropriately, so let's see. nRT sub C ln V2 over V1 nRTH ln V4 over V3. Well, of course, these are all negative. Let me see if... Okay, there's a sign mistake here which we need to correct. I will be back in a moment. So we discovered that we haven't made any mistakes. This is Q net. In order to make it work net, we have to put a minus in front, and that is going to take care of this negative temperature gradient. And ours will cancel. ln V2 over V1's cancel, and we are going to have T sub C divided by T sub H minus T sub C as the coefficient of performance of a refrigeration cycle. Now, let's iterated on the PV diagram and TS diagram. Also, here the area under this domain is network. And of course, area under this rectangle is QC. And for this cycle, we have one more step to complete. We'll just do the first and second law analysis of the general refrigeration cycle in the next segment on a clean board. Now we are going to perform a global first and second law analysis on this refrigeration cycle. Now let's start with the first law analysis. This is a cyclic process. Delta U is equal to 0. Because it's a cyclic process. Let me see. It's a cyclic process. Yes, we have inflow. All right. Okay, delta U is equal to 0 because we have a cyclic process, and this is equal to Q cold plus Q hot. Remember, we dropped the dots because we took the integral, plus work. All right, this is 0. So Q hot is equal to the minus in front, Q cold plus work. Whatever comes in has to go out. This is the first law. The second law says that delta S is equal to 0. It is Q hot over T hot plus Q cold over T cold. Now, Q hot is minus Q cold plus work minus Q cold over T cold. T hot, I'm sorry, Q cold over T hot minus work over T hot plus Q cold over T cold, and what we are after is Q cold over work net. We are going to rearrange this. Work over T hat is equal to Q cold 1 over T cold minus 1 over T hat. This is equal to Q sub C T hat minus T cold divided by T hot times T cold. This is work over T hot. Cancels. And we're coming to an expression very similar to what we see on the light board. Q sub C over work is equal to T cold over T hot minus T cold. This is the black box analysis result. This is the Carnot refrigeration cycle analysis result. All right, coefficient of performance of a Carnot cycle or a reversible cycle is directly related to the temperature gradient between 2 points and the temperature of the cold spot where we wish to remove the heat. So if we want to, of course, those temperatures are absolute temperatures. We have to use Kelvin scale for temperatures. When we are differentiating the temperatures, the Kelvin correction factors cancel out, but still, when we are dividing numbers, we have to be careful to use absolute temperature scales. So this also sets a border, a thermodynamic boundary of how high a coefficient of performance can be given the temperature of the coldness that we want and the temperature gradient between the hot and cold domain. So with that, now we have a set of boundaries, a set of tools that we can analyze power cycles as well as refrigeration cycles. Now in the next segment, we are going to learn the steam engine, the Rankine power cycle.